Alright, so hi everyone, welcome to this video. So in today's video, let's talk about logic gates. In a while, let's get to know what these logic gates are, at the same time understand how they function. Welcome to this channel, Number Explorer channel. So, elect electronic circuits in computers are made up of thousands of logic gates. Logic gates takes binary inputs and produce a binary output. So they act as a building blocks to which they perform basic logical functions that are fundamental to digital circuits. So these logic gates are NOT gate, OR gate, NOR gate, AND gate, NAND gate, and the XOR gate. Okay, at the same time, this is how they look like. Okay, let us start with the NOT gate. Okay. This is the symbol for the NOT gate. It only contains one input to have an output of X. So in this case, we have input A with the output of X. So how the NOT gate or how this NOT gate works? Very simple. The output is just the opposite of the input. So let's say, for example, if we have the input of A, 0, we have 1 for the output. And if we have 1 for the input, we have 0 for the output. It's just completely the opposite. That is NOT gate. Next one is the OR gate. Okay, the OR gate now contains two inputs. We have A and B for this example, with the output again of X. Now how OR gate works is just simply the addition of the inputs. We have A plus B. Let's say, for example, we have the inputs of A and B, they're both 0. If we try to add them together, that will give us the output of 0. In this case, if we try to add them together, that's also 1. Same here, that's also 1. And lastly, the sum of the 1 plus 1 is equal to 1 in the binary world. Okay? So we just have to take note that in this topic or in this world of binary, 1 and 1 when added is equal to 1. Okay, that's it. That is how the OR gate works. Next is the NOR gate. Okay, the NOR gate is just the opposite of the OR gate, meaning the output of the NOR gate is just the opposite of the output of the OR gate. Let's say, for example, what I mean is, if I try to have the output of the NOR gate, let's say, for example, if we have A and B, they're both 0. If I try first to get the OR gate, means we have to add these two together, that is 0, correct? However, you'll just have to get the opposite of 0, which is equal to 1. Okay, in this case, if we try to add this, that's equal to 1, and again it's 0 for its opposite. Same here, it's equal to 1. We have now 0 for the output. In this case, it's 1 as well, and again 0 for the output. So therefore, we have 1, 0, 0, and 0 for the outputs of the NOR gate. Okay, just take note that the NOR gate is just simply the opposite output of the OR gate. All right. Next to be followed is we have the AND gate. Okay, very simple. If we add for the OR gate, in the AND gate is just the product of them, meaning just simply multiply the inputs A and B. For example, we have this first inputs that will provide the product of 0. Same here, equal also to 0 again. Also here, equal to 0. And this is equal to 1. Okay, it's just simply the product. Okay, the product of the inputs. Okay, That's the AND gate. All right. Next to follow is just the NAND gate. Okay, same with the OR and NOR gate. The NAND gate is also the opposite of the AND gate, meaning whatever you get for the output of the AND gate, just get its opposite to get the entire NAND gate. For example, if I try first to get the AND gate of these inputs, so their product is equal to 0. In this case, it's just the opposite of 0, and that's equal to 1. Next, that's also 0, and again, it's 1 for its opposite. Same thing here. And lastly, it's equal to 1, and we have now 0 for the output. So therefore, we have 1, 1, 1, 0 for the outputs of the NAND gate. Just take note that it is just completely the opposite output of the AND gate. Alright? The last one is the XOR gate. Okay? XOR gate, it's very simple again. Because you don't need to add or multiply here. I happen to find out the very simple keyword or hints or guide to get the outputs of the XOR gate. And it says that like inputs, that's 0 for the output, and like inputs, that's 1. For example, here we have inputs A and B, they're both 0 here. So therefore, as they are like inputs, it's gonna be 0 for the output. Here, they are now unlike inputs, that's 1. Again, unlike, that's 1. Like, that's gonna be 0. Okay, that's the XOR gate. So again, to go back, we have these 6 logic gates, the NOT gate, OR gate, NOR gate, AND gate, NAND gate, and the XOR gate. Now, I want you to remember their symbols, as we would need to use these symbols in a while in answering a problem. Also, you will get to understand further how they work by answering a question in the next few slides. Let us try to answer this problem. This is actually coming from the IGCSE ComSci subject in the test of February to March or March, just the year of 21. This one, okay? So this is from question 5 of that test, and it says that to state the single gate or logic gate that produces the truth table of the following. Okay, so the goal here is to be able to determine what kind of logic gate is applied in each of this truth table. Okay, let's go for the first one. Okay, so here you just have to figure out what logic gate here by just simply trying every logic gate and finding out what is the exact logic gate being used in here. But let's try to test the NOT gate. Of course, clearly it is not NOT gate because it is having 2 inputs. Again, NOT gate only contains 1 input. Therefore, it is not a NOT gate. Let us also try with the OR gate. Now for the OR gate, it says that we just have to add, correct? If I try to add the first inputs, 0 plus 0, that's 0, right? It says 1 here, so therefore, it is completely or clearly not a or not an OR gate. Okay, how about the NOR gate? Let's try NOR gate. For NOR gate again, just simply get first the OR gate And whatever the opposite of the output of the OR gate, that's NOR gate. So if we have 0 plus 0 here, that's 0, it must have 1 for the NOR gate. We have the correct answer here. Next one, we have 0 plus 1 for that one. It's equal to 1. It must have 0 for the output for the NOR gate. However, it says 1 here. So therefore, it also not a NOR gate. Okay. How about the AND gate? For the AND gate, just get the products. So we have 0 times 0, that's 0. It says 1 here, so therefore, clearly not a AND gate. Alright? How about this next one? Let us try with the NAND gate. So we have here 0 times 0 for the first input. That's going to be equal to 0. However, for the NAND gate, it must have 1 output. Let's check. How about this one? That's equal to, that's 0 times 1. That's 0, and again, it must have an output of 1. Okay, check. Next one. How about if we have this one, we have 1 times 0, that's equal to 0. It must have an output of 1 for the NAND gate. Lastly, we have the 1 times 1, that's 1. So therefore, it must have an output of 0. So therefore, we have 1, 1, 1, 0, which is the correct output for this truth table. So therefore, this is just using this logic gate is the NAND gate. So NAND gate is the answer for the first truth table, right? How about this next one? So we have here another truth table. Again, clearly not a NAND gate, okay, because it contains 2 inputs. How about the OR gate? If I try OR gate here, so we have 0 plus 0, that's 0. Let's check. Next, clearly equal to 1, let's check. Next, 1 plus 0 is equal to 1, let's check. And 1 plus 1 is equal to 1. And again, it says here 0. So therefore, it is not in OR gate. Almost OR gate. However, it is not in OR gate. So if we try also the NOR gate here, it must have equal to 1. This must be 0, 0, and also 0. So we have 1. It's not also. So therefore, it's clearly not a NOR gate. Right? How about the AND gate? For the AND gate, that's the product, right? So we have 0 times 0. That's okay, check. But this times 1, that's 0. It is not. So therefore, it is not a AND gate. How about the NAND gate? NAND gate, we have 0 times 0 is equal to 0. So it must have 1 for the output. But it's not 1 here. So therefore, clearly not a NAND gate. Okay. Next one. Let's go for, let's say, for XOR gate. Okay, XOR gate, it says that like inputs, that's 0, and like inputs, that's 1. In this case, clearly, we have like inputs, 0, and like inputs, that's 1. So clearly, it is a XOR gate. So that the answer for the for the second truth table is just simply the XOR gate. All right. Next one. The last a truth table. So again, not a NOT gate. How about the OR gate? So again, we have the OR gate, 0 plus 0 is equal to 0, but it is not 0. So therefore, it is not a OR gate. How about the NOR gate? Let's try again NOR gate. So NOR gate, so we have 0 plus 0, that's 0. It must have 1 for the output. Let's check. Okay, next we have 1 plus 0, that's 0, that's 1. It must have 0 for the output. Let's check again. Next we have 1 plus 0, no, here. Again, we have 0 plus 1 here, so I'll check. Again, also here 0 plus 1. 1, it must have 0. So, and lastly, we have 1 plus 1. That's 1. It must have an output of 0. That's also correct. So therefore, clearly, this is a NOR gate. Alright? So I hope this is clear and understand how the logic gate works. Just simply try to test every gate to find out which gate is being used in a certain truth table. So with that one, we're able to answer the number 5 question, of the IEC GSE exam. Okay, and it contains 3 points or 3 marks. Okay, how about if we try to have this um, question? This is also coming from the ICGSE, but this was from May to June, the year of 2020. Now the problem here, it says that to consider the given logic statement. So this one, okay. So we have this one. So in this case, we are now gonna draw the logic circuits. Okay. So this is now the time when you would have to consider how the symbol looks like to each of those logic gates. Okay. So we are given here a logic statements. As we can see here clearly, if I'll try to zoom that out or zoom that in rather, we have here 3 parentheses. Okay, so the technique here again is same with math. You will have to work first what is inside the parentheses. So we have A XOR B, followed by the A XOR B and C, and lastly we have the A XOR B and C or not Z. Meaning, if I try to figure out the number of gates here, we have to base on the given conditions. So the first gate is the NOT gate, we have the OR gate, we have the AND gate, and the XOR gate. So clearly, you are producing or you are to expect 4 gates in our logic circuits in the be drawn in this area. Okay. All right. Let's say, for example, let us have the first one first. It says A XOR B. So you have now the inputs here A, B, C that you are to follow. First is you are to combine the A and the B. Just simply add a line there. Okay. But the A and B are connected using the XOR gate. So you have to recall how the XOR gate looks like. And it says this is this way and then that way. Okay. One. Okay. So let's try to draw that symbol here. Okay, we have these 2 inputs. And we have this first curve, another curve, and we will then draw that way. Okay. Okay, that's it. Okay, this is now your very first gate, which is the XOR gate. All right. So next is we have the next statement here is to combine the A XOR B and Z. So as we know, the A XOR B is now in this gate, the first or the gate number 1. To combine this gate number 1 with the input C using the AND gate. We have the input C here. Let's say you have that input C there. Okay, combining to the first or to the A0 gate, the XOR gate or the A0 B gate, that one. But this is in the AND statement or AND gate. And again, if you try to recall, the AND gate must look like that way. And then that way. It's like a semi-oblate. Anyway, it does have to draw properly and you are trying to answer this kind of problem. Again, we have this two gates. You have a straight line right there, and then just simply like an oblate, a half of or semi-oblate. Shoots. Okay, there. All right. That's it. The last one is to combine now. We have the A XOR B and B combined with the OR, not C. However, first is you will need first to draw the gate for not C. Okay, so I will now name the second gate as, let's say, gate number 2. So we have gate number 2 here. Again, this refers to the AND gate. All right. So first is, before you go to the OR not C, you would need first to have the gate for not C. So not C, again, the NOT gate is just simply that way. That one, okay. So we have to draw this kind of gate from your C input. I'll try just to create like a small detour here, a line here from the C, and then I'll try to draw here the NOT gate. That one. Okay, just a very bad drawing. However, make sure to draw it properly when you are trying to answer this kind of problem. All right, so let us try to add more line here. I'll now call this as the gate number 3. I'll just put the 3 over here. And then lastly, we're gonna combine all together all of this, which is just represented by the AND gate or gate number 2, and then to combine that one with the NOT C, we have the gate number 3. So again, we have that one. Let me try to draw it again here. Okay, and again, the statement says it's gonna be OR gate, and again, the OR gate is looking this way. We have the 2 inputs, like the curve something. Okay, and then we have that kind of symbol. Anyway, just draw properly in a while. All right, so in here we have this 2 inputs, that one. Make it straight, and then like a curve here. All right, that way, and then you will have to have that one. All right, okay, this is now the output, but it must go to the X actually. Okay, you can also just draw the X here, whatever you ended up. Okay, that's it. So therefore, this is now the logic circuits of this logic statement. Okay, from the A XOR B, that one, the gate number 1, to the AND for the A XOR B and Z, gate number 2, NOT C, gate number 3, and the last gate is gate number 4, which is just simply the answer for everything, the A XOR B and C or NOT C, to have the output of X. Right? So it's very important to understand or to figure out or to recall how those um, logic gate symbols look like, to be able to figure out how to draw the logic circuits. Okay, just simply follow whatever given statement in the logic statement. All right. Now, okay, using this, okay, we're going now to answer the next one, the next problem. Okay, okay. I will need first to screenshot this one as our reference. This is the answer for, I'm gonna put it, let's say for example, that way. Okay, so I cannot erase my writings in, alright, mm-hmm. Alright here. Okay, so to reference or to answer this one, I'm gonna reference this right here. Alright. Mhm. Okay, there we go. So we have here again the input A, B, and C from our previous drawing. Now we're gonna do the working space, or we're gonna go the complete the truth table rather, until we arrive with the X. Now, a while ago we were able to capture, or we were able to have 4 gates, right? So I will now draw. I'm gonna need like 3 gates here. Okay, that one. So we have now your first gate, your second gate, your third gate, and the fourth gate is the X. Right? Now, the first one is the first gate here. It says we have the A XOR B. Okay, we have here again the A XOR B. Right? Uh, okay. Mhm. So for the A XOR B, we have to make use of the A and B. And again, for the A XOR B, uh, we have to have the like sign 0 and like sign 1. So the first one, they have like sign, that's gonna be 0. Okay, so we have still like sign 0, and like sign 1, and like sign 1, and like sign 1, that's 1, like sign 0, and then like sign also 0. All right, the next one, it says the A XOR B not and C, meaning whatever you have for the A XOR B here, and just have the AND logic statement for the C. Now we have here again, so we have now the A XOR B, right? This is your A XOR B, the number at the first gate. Just combine that with the C input and just get the AND gate. So get on the products. So we have the product of this is 0. This is also 0. Another 0. Another. This is now 1. This is 0. This is 1. This is 0. And this is also 0. Now for the third gate, we're able to find out a while ago that it's just gonna be the A XOR B and C, or the not C first. Okay. The third gate refers to the not C gate. So meaning you're gonna be needing to base it on the C, and then just uh, look for the not gate of C. Okay. So if this is 0, it's gonna get 1 for the first input of here. 0, 1 is gonna be 0. 0 is equal to 1. 1 is 0. 0 is 1. 1 is 0. 0 is 1, and then again 1 is 0. Okay, and lastly, for the last one, for the fourth gate, it says okay, A XOR B and C or not C, or just the fourth gate a while ago that we have discovered. So if we try to go back again here, we're just referring to the fourth gate, okay, which is the OR gate of the gate number 2 and the gate number 3. So to go back there, we'll refer to the gate number 2 and 3 and get the OR gate of those two gates. So gate number 2, number 3, just so these gates, and then just get the OR gate. So adding the inputs of the gate number 2 and the gate number 3. So to add, that's going to be equal to 1, this is 0, this is 1, this is 1, this is equal to 1 again, this is 1, this is 1, and then this is 0. Therefore, this is now the correct outputs. Okay, so all in all, we have this complete truth table for the entire logic statements required in this number 6 question of the ICGSE May June last year exam. All right, so that's it.